Hi guys, today I'll be showing you how to make the schematic and layout for Pseudo NMOS inverter. So open up your schematic tool. So file new schematic and we'll name it as, create a new folder and place it inside that. Say sudo. So I'll come back after I draw the schematic. So this is your Pseudo NMOS inverter. Just change the name of the ports to whatever you want to name it as. Say this is V out, this as V in, and choose each device and change the asm underscore model from PCH to P for PMOS and NCH to N. Now set the W by L ratios of your NMOS and PMOS. So I'll take the W by L ratios as L as 0.4 and W as 0.6 for both the transistors. You can change it according to your design, doesn't matter. 4 and this is 0.6. Right, so this is your schematic. Now on the top you'll see add, generate symbol, choose these two, enable these two boxes on the left and click on OK. You'll get this, then click on check and save. After that you can close the schematic. Say yes if this pops up. Now file, new schematic. In the same folder, instead of the name inverter, save it as inverter underscore test. You can name it as anything. Just create a new schematic. In this, go to add, instance, choose symbol, and choose the first schematic, the block which I had made. This one. This is the MGC component which I had first created in the previous schematic, and you'll get this block, right? So whenever you have it's happening like this, just click on escape or you can press on cancel over here. Right, now just create the test cell of your Pseudo NMOS inverter. I'll come back after I finish the test cell. So this is your test cell. Make the required changes for this. Right click, edit object, and this delay will be 0 microsecond. Then period is 50. Pulse value is 3.3 volts for us. That's our input voltage. Don't change anything else, and you have width over here as 25, not 20, so that will have a 50% duty cycle. Okay, then here the right hand side VDD is 3.3 volts for our module which you are using, that is the TSMC 035 module. So 3.3 volts and click on OK. Click on simulation, new design configuration. You can give any name over here, so I'll give transfer. So this is the transfer care. So transfer C, click on OK. OK. Now go to analysis on the right side, click on DC, uncheck the OP. In the sweep type on the right, choose source, click on the small icon and choose the pulse. Then start from 0 to 3.3 volts, volts with a step of 0.001. Fine. In the left, now go to includes, left hand side, click on the small icon on the right and press on this small blue color browse location map models and choose the file tsmc035.mod depending on which technology you want to use. Click on OK. Then go to outputs, click on the selection for schematic box over here, then go back to your schematic window, click on this, holding control choose the other wire also, then go back to your the simulation window, And this analysis will be all. Task plot, this is voltage, and click on add. Say OK and run. So after the simulation is done, you can see that the current simulation will be completed. This line will be up. You'll get this line. Then go on the right side, click on view waves. So this is your transfer characteristics. This is your output, this is your input. Now we want these two overlaid on each other. So click on this, choose both of them, right click, plot overlaid. So this is your transfer characteristics. Where the input meets the output, that will be your threshold voltage. So right click, add cursor. So wherever it meets, there will be a threshold voltage. Okay. So this is your transfer characteristics. Now I'll show you how to do the transient analysis. Now in the simulation itself, go to analysis, change this from DC to transient, and give here right side a start time to 1000 nanosecond. Click on OK and run. So after the simulation is done, you will get this pop-up, that is, it will be written current simulation completed. Then go to view waves. So click on the small plus icon, trans. Here your input and your output. So now if you want to see the, you don't need to see peak to peak. If you want to, just click on these two, choose both of them, choose the small open measurement tool. Here in this, choose peak to peak, remove the average, say apply. You'll get the peak to peak voltage. Now if you want to find the frequency of it, instead of measurement as all types, go to frequency domain, sorry, time domain. In that, choose frequency, say apply. Okay. So that is your frequency of the output, frequency of the input, input peak to peak and output peak to peak. Okay. So this is your transient analysis. Now I'll show you how to do the layout. Now close this window, open the schematic tool again, DA_IC, file, open your first one, I mean the in which you do the transistor model, that is this inverter, say OK. Change the transistor, right click on the transistor and say edit object, change this from P to PMOS and N to NMOS for the other transistor, and say OK and check and save this, close it. Open your layout tool, okay. So say file, new, layout. In this, go to component on the left. Here choose your pseudo, this the first block, and say OK. Copy this, paste it, and change the name to say layout. You can give any name, that's okay. And click on this box on the beside process. Then in that, the same blue color, browse location map, this process TSMC035, the P icon which will be on the left, say OK. Same thing for the rules, the blue color box, that rules TSMC035 dot rules, this one, which are depending on the technology you're using, say OK. Click on OK. So you'll get two windows. One is your layout tool, layout window. This is your schematic window. Go to the schematic window. In that, you'll have to do three settings. You'll have to change three settings for the layouts. So on the top, you can see setup. In this, go to SDL. Click on the small SDL port styles and say setup. In this, choose 49 metal 1. When you click it, it changes, so make sure you have chosen 49. Width is 3, height is 3. Say OK. Click on OK. The second thing is setup, pixels assemble. In this, enable the fixed pitched grid. Enable fixed pitch grid. Change it to 0.5, 0 to 0.5. Say OK. The other thing is go to file, MGC, setup. In this plus, click on this plus icon. Oh wait, before that, click on default on this left right tiling. And in this, the other thing is go to display, rulers/grid. Change the snap grid coordinates from x 0.5 to keep it as 0.5. Initially it will be different, so make sure it is 0.5 and y is 0.5. Say OK. So then you will have your layout and schematic placed side by side like this. So now go on to your schematic and click on instantiate. Choose one device, take one transistor and say in inst, that's instantiate. It creates an instance. So place it like this. Then choose the other transistor, say inst. Okay. So this is your two transistors. Now choose the input and say port. Only for the transistors you will have to do instant, and for all the input ports and grounds etc. you'll have to do port. So click on the wires and say port. You'll get this blue color box. Say for V out, then for ground, that's one. This is for your VDD. That's it, right? Yeah. So now you can close this, go to your layout window and zoom to fit. So now we'll place the metals. So first I'll place the V out. Zoom in, click on metal over here, easy edit, shape, and choose the 2 points. This thing should be completely covered with metal, the 4x4 box inside the transistor. So cover it completely. Click on the down arrow, then you can add it here. Zoom out, then place this blue color box on the metal. Click on that and make sure you unselect all before you do anything with the components, with the placements. So click on this and there's a small icon on the left, say move, and place it inside the metal. It should be completely covered by the metal. Now zoom out, that is your V out. Now we'll do the VDD and ground. So choose metal, shape. So choose the starting point from there, and it should be a minimum length of this substrate, this much, that is 26 micrometer, and make sure the and choose the width as 8 lambda. Okay, so unselect all and similarly place the port on it. So make sure it is completely covered, and now we have to connect the transistor to the VDD. So click on metal, shape, and choose that corner and the other corner. If you choose 2 points while making it, then it gives you a rectangle. If you choose 1 point, you will get a square. Say what I mean is, so if you choose 1 point, this is your 1 point, then you can make a square. If you choose 2 points, you will get a rectangle. Okay. So when you are overlapping between metals, the minimum overlap should be 0.5 micro. So I have taken 1 micro. Okay. So now similarly do the ground. Metal, shape, should be a minimum length of this substrate, and 8 lambda. Now similarly place your port on it. And similarly connect your transistor to the ground. And select all. So you can see you have made the connections and you have your input left. So to make a connection between poly and metal, you'll have to create a wire. So I'll show you how to create. First extend this poly. So take it out a little bit here, then choose 2 lambda. Okay, so after you have done this, you need to have a 6 by 6 lambda block at the edge of the corner here at the ending. So make a 6 by 6 lambda block. It should be centrally placed and no other material should be inside it. I mean, this poly should not be inside the 6 by 6 lambda block. So 1, 2, 3, 4 here. So that's a 6 lambda block. So this small, the other extension of the poly should not be inside it. As it is the same material, you don't need an overlap. Okay, so now this is poly block. Now inside that you have to place a contact to poly. You can see the one below the poly. Click on it and say shape. So you should place a 2 by 2 block at the center. So here like this. Okay, say unselect all. Now click on escape for a bit. Then click on this contact to poly, tools, iRoute, and click at the center. Then it will disappear. Say right click, set wire width to 4, new width is 4, and say OK. And drag it to the left or right depending on how you want it. After you are satisfied with the length, say space, you'll get this purple color blocks and purple color block, and double click twice and double click, that's it, and select all. Now place that metal on that port onto this, and it should be completely covered by the metal. So that is your input, that is your VNO here. So when you see it, it will be highlighted over here, right? So here and select all. Now your left is this, these yellow lines are the virtual lines which shows you which are the connections left to be done. You know that in the pseudo NMOS inverter, the PMOS gate is grounded, so that is what it is showing. So we need to connect this poly to this metal. So we'll have to make another poly to metal contact. So extend the poly. Like you did last time. So here you're not optimizing the area, so I'm not very considerate about placing it nearby each other so that it occupies less area. This is just for understanding. So 6 lambda. Okay, then inside that place the 2 cross 2 contact to poly and select all. Click on this, tools, iRoute, one click, then right click, wire width to 4, say OK, and drag it down. So that is your, now drag this metal and place it on this, sorry, my bad. Choose metal one, shape, and cover this. So the yellow line is gone. So this is how it will look. I'm using too much area, but yeah, you can reduce this area over here, you can reduce this poly, you can reduce this poly also. So this is just for understanding. Now we have connected all the inputs, ground, but we didn't connect the body. So for that we'll have to place the well contacts on the top. You can see the body of the PMOS is connected to VDD. So the well contact will be between VDD and the PMOS transistor. And similarly for the NMOS, it will be for the ground and the NMOS transistor here. So to make a well contact, you'll have to right click, add, layout, and click on this blue box, browse location map. In that library, tsmc035 underscore via, double click it, and you will see NWell contact and PWell contact. So take the NWell contact, say OK. Okay, and place it in such a way that you can see the dotted lines. Each dotted line represent 0.5. So on the top it should be one dotted line and below 3 dotted lines to be seen. So why, I'll tell you. So unselect all, you can go to view, peak area, and just you can see the internal structure how it is. So this inside green color block, this one, the inside one, it should be completely covered by metal, and this whole contact should be a combination of the substrate, the dotted lines, and the metal. So if you place it like this, it will be correct. You can place it with a 6x6 metal also, but I find it better like this. So view, you can unpick it, you don't need it. Okay, so select all. So that is your NWell contact. Now place your PWell contact. To place your PWell contact, the same thing, right click, add, layout. So when you have previously placed your NWell contact, so it will already get an NWell contact when you click on layout. Now to go to PWell contact, press Q, and you'll have this pop-up, and that drag it up, and then change this from NWell to PWell. And say OK, and it'll get placed somewhere. So just find it and move it to the, so it's over here, say move and place it over here. Similarly, 3 dots on the top, 1 dot on the bottom. So this is this 1 dotted line on the bottom and 3 dotted lines on the top. Save. That's it. So that's done with your layout. You can unselect all. So this is how it will look. So to do the DRC and LVS, go to File, Export, and GDSII. So this will create a file so that you can compare your schematic and the rules. Similarly for the LVS, you can compare it with your previous output, I mean the layout and your schematic which you have made. Click on the small box on the right and go to the same folder where you have made your layout. So user, where is sudo, and here place it as say test.gds, save it as a .gds file, say OK. In this left hand side options, choose these two on the top, enable these two and say OK, say OK. So that will create your GDS file. Now go to tools, calibrate, run DRC. It will take some time, and here close this window. In rules, change this rules to $capital rules and click on this 3 dots and choose the TSMC035 technology rules depending on your technology. After you have chosen the correct rules, it will become green in color. Then go to inputs on the left, disable this export from layout viewer and click on the 3 box on the right, the small one, and go choose that GDS file which you have just saved. So that'll be your, where is sudo test.gds, say OK and click on run DRC. If you have done any mistakes while creating the layout, it will be shown in this. So see, you can see the tick mark saying that it is correct. If anything is wrong, you will get a cross mark. Okay, now we'll check the LVS. You can close this, tools, calibrate, run LVS. So close this box. Similarly, just make it as $RULES. Click the three dots. Choose the tsmc035.rules. Inputs. Here disable this and choose the .gds file. Test.gds. Okay. And in this you'll have to add another file. So here layout you can see, right? Go to the netlist under the other one beside it. Click the three dots and open the Pseudo folder, the where you have placed it, and in that the test cell, this is the inv underscore test. In that you had made one new design configuration, right? That was your transfer underscore c, transfer c for me. In that you'll have one file named netlist.spi. Click on it, add, and OK. You'll get the file only if you do the transient response. If you do the transfer characteristics, you'll not get it. After you have added the SPI file, click on this three dots for the top cell here and say whatever you get, click OK and say run LBS. So if your the transient response, if your layout and schematic match, you'll get this. So ports is the number of inputs, outputs, etc. So to check what you have got from your transient response and what is your layout, just on the left you can see schematics. Click on it. So this one is created by your layout file, this block, and the right side block is created by your transient response. So you can see it will be quite similar. Okay. So yeah, this is your pseudo NMOS inverter. So thank you. So if you have any other queries, you can let me know. Thank you.